Yes, sir. Good afternoon to all participants from various institutions, industries, research scholars, students, and the faculty members of Anna University gathered here. On behalf of IES, I take immense pleasure in welcoming the speaker of this session, Mr.S.Patrison, sir, Managing Director of Adroit Fantech Engineers, Chennai. He started his career in 1990 and involved in design of light, medium, and heavy duty fans, and also in ventilation systems and in air pollution controlled equipments. He has more than 30 years of experience with several responsibilities include marketing, engineering, production, erection, and commissioning and project departments. He started Adroit Fantech engineer in the year 2004. His specialization includes detailed engineering of fans and blowers, designing of ventilation system and evaporative cooling systems, designing of air pollution control equipment like back filters, cyclone separators, multi-cyclones, packed bed scrubbers, and venturi scrubbers, and also in the designing of duct systems, vibration analysis and condition monitoring of rotating equipments, and also in the dynamic balancing and inside balancing of rotating equipments, failure analysis of fan, blower, and the systems, performance testing of fan and blowers, and performance testing of different equipments and production techniques of blowers, fans, air pollution control equipments, ventilation system, and more. And we are very happy to inform that he was involved with Institute for Energy Studies to study the fan performance in many energy audit too. Now I request you to deliver a technical talk on avenues for energy conservation in fans. Over to you, sir.
Yeah. Good afternoon, everybody. I take this opportunity to thank IES Anna University for graciously giving me this opportunity to deliver a speech on energy conservation on fans and blowers. With the advent of energy crisis and increasing price of fuel, industries are forced to conserve energy to reduce their energy bill. It is possible to conserve energy with variable indigenous technology and power techniques. Through our experience, we understand about 10% of the total energy can be conserved by modified operational practice, and about 20% can be conserved by process modifications. One category of equipment that has received little attention from this standpoint is the industrial fans. Fans can be a major consumer of energy throughout the operation. So I just give some introduction on the fans and types of fans, and thereby we go in detail about how do we study a fan and conserve energy. How to go to the next slide. Okay. Fans and blowers are equipments that are used to move air for industrial process and ventilation. The difference between fan and blower is the fans will have specific ratio up to 1.11 and a pressure rise of 1136 water column, whereas blowers will have a specific ratio between 1.11 to 1.2, where the pressure rise shall be 1136, that is 1136 water column to 2066 water column. Anything above this specific ratio and pressure rise would be called as a compressor. So now we go into the types of fans. There are a few types of fans, like we can call axial flow fans and centrifugal fans, which are widely used in the market. There are other types of fans also, like mixed flow fans, or you may call it as impulse type axial flow fan, or the cross flow fans. Now the major contribution in the industry are centrifugal fans and axial flow fans. So axial flow fans can have another three types, which will be propeller, tube axial, and vane axial. The centrifugal fans, they are of different types depending on the blade angle and configuration. So they can be radial straight bladed fans, radial tipped fans, forward curved fans, backward inclined blade fans, backward curved fans, and aerofoil bladed fans. So though they are centrifugal fans, they may be named after the application. Like for example, in a power plant boiler, we may have a ID fan, we have a PA fan, we have a FD fan. But all these are centrifugal fans, but they are named after their applications. Similarly, propeller fans are named after either circulating fans or exhaust fans. Tube axial fans are also generally called as axial fans, or they may be otherwise named by the application. How to differentiate? Axial fans are so called as the flow enters axially and they leave the fan axially. That is, the flow at inlet and outlet of the fan is parallel with the shaft axis. So it's almost like entry and discharge are 0 to 180 degree. The centrifugal fans have an axial entry and the flow leaves the fan radially. That is, the flow at inlet is parallel to the shaft axis and the exit is at 90 degree from the shaft axis. So they may be sometimes even called radial fans just because of the entry is axial and the delivery is radial. So this is how a centrifugal fan will look and the axial fan will look. So the components, the axial fan classifications are: the air enters and leaves the fan with no change in direction. These axial fans, they can normally handle high flow rate at low pressures. The axial fan components shall be motor, blades, hub, casing. So in the case of propeller fan, it is only the mounting bracket, blades, and the motor. In the case of tube axial fan, this propeller fan may be installed into a tubular casing with the motor and the hub. The vane axial fan will be similar to the tube axial fan with a vane at the inlet and outlet or either in one place. So these vanes will help the air, it will help as a air straightener to the flow. Tube axial fans, normally their pressure range is only up to or limited to 100 mm, but they can give a very high flow with high diameters. Their efficiencies are much limited to 65%. The wheel in a cylindrical housing with the close clearance. Only if the close clearance is maintained, you get a better efficiency, which I will show you in a picture form in the later slides. These vane axial fans, they are similar to a tube axial fan, or these tube axial fans are incorporated with the vanes, guide vanes, for providing a straightening to the airflow. The efficiency is in the range of around 55 to 60%. The pressure range can go up to 150 mm water column. As I told you earlier, these propeller fans are often used in indoor application like exhaust fans, and even your ceiling fans are also called as, they are also come under the propeller fan category. Runs at a very low speed and moderate temperature. This can handle a huge volume of air with a very minimal pressure, and the efficiencies are very low, that is even below 50%. Now, coming to the application of the axial flow fans, they are widely used in air conditioning and ventilation, that is HVAC, and they are also used for fume exhaust systems. They are used as a booster fan in the duct systems, and similar fans which are now called as jet fans are used in car park ventilations and all. These vane axial fans are most widely used in tunnel ventilation and in the mine ventilation, because that is a place where you require more thrust and more pressure drop requirement will be there. So, in case of a centrifugal fan, the airflow changes direction twice, when it enters and when it leaves. It can generate high pressure at per stage at lower flow rate. Number of stages are limited, whereas in the axial flow fan, the number of stages can be more. But we have seen fans with even we have made fans even with 5 stages and been working successfully. Smaller size can be made even on a single rotor shaft, or individual bigger size fans will go from one fan to the other fan. So 5 fans at a stage, like in a mini blast furnace applications. As we discussed earlier, there are different types of blades in a centrifugal fan: the backward curve, forward curve, radial blades, backward inclined blades, aerofoil blades, and radial tipped blades. So the components are impeller with the hub, the motor, of course the prime mover, the casing, that is the spiral casing or the volute casing we call, the inlet cone, and the shaft. So these are the components for in a centrifugal fan, where apart from this you may have the drive pulleys and belt, or if it is going to be a couple drive, then you will be having the coupling and the coupling guards. The centrifugal fans can achieve high pressure. So pressures of even up to 3100 or 3200 mm is possible in a single stage centrifugal fans. But it depends on the volume also. Flow drops directly with the head. So that means when the flow is drooping on the curve, if you see the curve and the flow is getting reduced drastically, the head, it goes drastically with the head. Useful in appliances that are not prone to clogging. So here there there should not be any clogging, because this fibrous material or something like that cannot come through this fan. Centrifugal fan blade design. So you can see in this picture, there is a casing, spiral casing, and there is a rotor inside, and you will find the blades. So you will find that there are 6 configurations here, and you can see the blades there. Radial blade. So the radial blade is a straight blade, nothing but a straight blade. It is attached to the hub, and these straight blades sometimes may have a shroud in the impeller. Normally the impeller will have a back plate, blade, and a shroud. These are the 3 components in a centrifugal fan impeller. So in a straight blade impeller, where some amount of higher granular material is coming into the impeller, we offer without the shroud. So it is called as an open impeller. If there is a shroud, it is a closed impeller. So this impeller have a very low efficiency, and but they can handle material. The blade is having an inlet and outlet angle of the blade will be 90 degrees. So something to achieve a better efficiency, but something similar to this radial fan is a radial tipped fan. So the radial tip fan will have a curve at the entry of the blade, where the entry of the blade is not at 90 degree. So it gives a smooth flow to the flow for the medium, but the exit angle would be 90 degree. It is radially tipped. So these can be used for higher efficiency. Just to improve the efficiency, we are giving this application, and I will tell you the application in the next slide, where I will explain. So backward inclined blades. So these backward inclined blades will have an inlet and outlet angles less than 90 degree. It is against the rotation. So this has a good efficiency. And when these blades are formed with a curve to give a smooth passage, they are called as backward curved blades. And to make the flow more better and smooth, we make an aerofoil blade, and these aerofoil blades have a better efficiency and low noise levels. The forward curved impellers are mostly used in HVAC applications. They can occupy lesser space, and the blade angles are always above 90 degree. And these are most of the time, the otherwise name is called as a squirrel cage impeller. So here we can demonstrate what would be the flow for pressure, temperature, airstream, efficiency, and for all these impeller type. The radial will have a medium flow. It can give high pressure because of the blade angle. It can withstand high temperature. The airstream, it can even handle contaminated air. The efficiency is very low. As flow increases, the power increases. If you go to the other configuration of the radial tipped impeller, they will also handle the same medium flow, high pressure. The temperature also, they can also handle high temperature. They can handle contaminated airstream. The efficiency is little higher than the radial impeller, but not more than the backward curved impellers. So there also, as the flow increases, the power increases. Forward curve impellers, they have a higher flow, but a limited pressure, that is medium pressure, not more than like 200 or 220. Their temperatures, they can handle only low temperatures. Airstream should be clean, because the number of blades there are very high. They range from around 34 to 64 numbers, depending on the size. The efficiency is medium, and as the flow increases, the power also increases. Now coming to the backward curve or backward inclined or even the aerofoil blade, the flow is high. They can handle high flow. They can deliver a high pressure. They can handle medium temperature. But on today's technology, going for high temperature withstanding material like SS310, you can go up to 550 degree temperature, operating temperatures, and anything at even up to 600 you can go. On using Impellers material, you can go even up to 700, 800 degree operating temperatures. So the airstream is both contaminated as well as clean. And in the contamination case, you may have to go for hard facing because these blades are having lower angle less than 90 degree, and their the angle of contact of the contaminated particle will be very high, so the erosion may take place. In that case, you may have to go for hard facing or some wear resistant material. The efficiencies are very high, particularly in the aerofoil fans, and as the flow increases, the power decreases. And wherever the dust application is there, we normally don't recommend aerofoil blades, as the aerofoil blades are a hollow section, and if there is an erosion, they can puncture the blades and the material deposits in the inside will increase the vibrations. Now the applications of various types of blades in the centrifugal fan and axial propeller and vane fans, vane action fans. Radial fans, various industrial application suitable for dust laden air and moisture air gases. Forward curve, they can handle only low pressure, so suitable for HVAC. Packaged unit, suitable for cleaning air. Backward incline or backward curve and aerofoil, they are used in HVAC, but they may be huge in size when compared to the forward curve in the HVAC. Various industrial applications, that is the process like FDID or whatever process industries, these centrifugal fans are used with the backward curve, backward incline because of their efficiencies. Propeller fan for air circulation, ventilation and exhaust applications. Tube action, again for HVAC, and they can also be used in drying ovens. Normally these tube axial fans blades are made of aluminum die cast, either gravity casted or now today it is pressure die cast. They can also be given in non-metal blades like nylon, GRP, glass reinforced polypropylene. They can also be given in polypropylene and other plastic materials. Vane axial is used in tunnel ventilation. They are little rugged because they are very roughly used and continuously operating with high temperature. The blades are made of aluminum alloy, and they have the vanes in the inlet and outlet or sometime only on one side, so which can straighten the air, thereby giving a smooth airflow. So here I am going to demonstrate on the individual type of blade in the centrifugal fans. Why we are concentrating more on these centrifugal type of fans is 85 to 90% of the process industry and the power consumed is only by this centrifugal fans. Whether you take it the cement industry, the sugar industry, wherever the boiler application is there, the metallurgy industry, the refinery, even the fertilizer industry. So these fans, centrifugal fans, they consume more than 85 to 90% of the power used in the process industry by the fans. So they have a rugged blade design, and because of the blade being 90 degree, they are called self-cleaning impellers, but their efficiencies are very low. So today, in today's technology, these type of impellers are not much used. They are being replaced with radial straight or radial tip or or backward curve. So what is happening is, if you go for a backward curve impeller, you may have to take care of the erosion, what I told you in the earlier slide. Used for material handling due to blade strength, moderate to high pressure industrial application. The power rises continuously to free delivery. That is, once if you don't have the resistance and the fan is at free open, that is free air discharge, the motor will overload. The radial tip is just a configuration of this backward curved and the radial blade. So the blade is radial at the outer edge of the wheel, curved in the direction of the flow as it moves inward. More efficient than radial blades, used for mildly erosive environment, higher pressure than aerofoil fans or backward curve fans. The centrifugal forward curve impeller, the blades are curved forward in the direction of rotation, that is, their angle is about 90 degrees. Low pressure used in HVAC application and also in our window ACs you can see. Lower speed than other centrifugals because of their lightweight construction. Single thickness blade, lightweight construction. Centrifugal backward inclined blades. Okay. So after the radial, you find the centrifugal backward incline. These impellers can discharge very high flow rate. Efficiency is slightly less than aerofoil design, but more than the radial tip impeller. Power reaches maximum near peak efficiency and then reduces towards the delivery. This is a very important point in a backward inclined blade. So at any point of operation, at that given temperature, or at the given temperature and at the given speed, this fan, even at free discharge, it will not overload, because when you go through the curve, the power curve will not be in the rising direction. At the end of the curve, it will drop back. So these fans are almost called as limit load fan. Consideration for use in application where aerofoil blade erosion concern. I told you in the previous slide, aerofoil blades cannot be used in application where it is going to handle dust. The reason behind it, it may erode the blade and the hollow space inside may be accommodated with the dust particles, and that may increase the vibration in the color because of imbalance. The centrifugal backward curve. These are having the blade angles less than 90 degrees. They are inclined and curved. The power reduces towards free delivery. These are also, in some cases, if they are not a high pressure, not a narrow impeller, high width impeller, then they are also limit load fans. Promote smoother flow than BI, that is backward impeller, backward inclined fan. These impellers can operate at a very high temperature and therefore require steadier construction than forward. But the temperature here are limited. You cannot go beyond 380, 420 on the backward curve impeller because of the stresses acting at the edge of the impeller. In that case, we would always prefer to go for a radial tipped impeller or a radial straight bladed impeller. The centrifugal aerofoil blades. The blades curves away from the direction of the rotation. That is, it is something similar to the backward curve. It is a backward curved impeller only. Only the blade is formed in the shape of an aerofoil, which improves the efficiency, reduces the noise level, and it can give the highest efficiency, relatively low noise, high structural strength. Power reaches maximum near the peak efficiency, then reduces towards the free air delivery. Again, these fans are also limit load fans, but not in all the applications. It depends on the width of the impeller. If the impeller is narrow and high pressure, it may not apply. Only if the impeller is having a broad width and with the lower pressures like up to 200 mm, then they may be a limited fan. So axial type fans we have already seen, but I would like to mention the pressure ranges here. So propeller fans generally operate at 5 to 50 millimeters water column. Inefficient, steeply rising power curve. So, their power increases when the pressure increases. It is the opposite of the centrifugal fan. Tube axial fan, propeller mounted in a cylindrical tube. The pressure ranges up to 100 mm water column. These also are overloading type. If the pressure raises, the power raises. Vane axial fans utilizes guide vane to recover the rotational energy up to 250, and they can give a pressure up to 250 mm water column in a single stage. And again, they are also overloading fans. As the pressure increases, the power increases. See the definitions. What is static pressure? The difference between absolute pressure at a point and atmospheric pressure is called static pressure. The dynamic pressure, rise in static pressure, which occurs when the air moving with specified velocity at a point is brought to rest. So, total pressure is equal to static pressure plus dynamic pressure. So, when we go for an audit on a fan, we should know that static pressure acts on all directions, and dynamic pressure acts, it may be called as velocity pressure, acts only in the direction of the flow. So the sum of these two is the total pressure. How to calculate the efficiency of a fan? The fan or blower, they have two efficiencies. One is the static efficiency and the other one is the total efficiency. So we have to calculate the static efficiency like Q in meter cube per second into pressure, static pressure in mm water column, or otherwise kg meter square. That is 1 mm water column is equal to 1 kg meter square. So divided by 102 into input power into motor efficiency. So motor efficiency, we can get it from the nameplate data of the motor or from the data sheet. So input power is measured. So what is 102? So you are converting the the output Q into H. By dividing it by 102, it becomes kilowatt. So you have on the upper side you have kilowatt, and below you have power in kilowatt. So this will give you the efficiency. So in the place of static pressure, if you are going to imply the total pressure, it gives you the total efficiency. Normally, when a fan procurement is made or audited, we have to take into consideration the static pressure, static efficiency only. So Q is always measured in meter cube per second, or they can be sometimes denoted in CFM, cubic feet per minute, or cubic meter per hour, or liters per minute, or liters per hour. The pressure can be, that is H, can be measured in mm water column, inches water column, Pascal, kilopascal, megapascal. So the power can be measured in kilowatt or in HP. So when you want to imply on the efficiency formula in HP, the power in HP, then instead of 102, you may have to imply 75. Fan characteristic. Fan characteristic can be represented in form of a curve under a specific condition. The fan curve is a graphical representation of a number of interrelated parameters such as the volume, the static pressure, power, and the efficiency. So whenever you want to study a fan, before going into the audit or performance study of a fan, we need to obtain the performance curve from the client, because they would have got the curves from the supplier in their records. So the curve is going to be very important for us to ascertain what is the design parameter of the fan and how the curve is being tested in the test block condition, and where do the fan operate on the curve now. Only based on this you can ascertain what you have to do with this fan to reduce the energy consumption. So this is the curve. So you are seeing a yellow line, that is the efficiency curve, but the blue line is the performance curve, which is volume versus pressure. So here the flow is mentioned, volume is flow is mentioned in CFM, and the pressure is in inches water column. So the blue line is the performance curve when you test a fan in a test block condition, that is as per IS standard or BS standard or AMCA standard. You need to have a test track, and you are creating a resistance artificially in the test track, and you are going to measure the velocity, static pressure. The velocity is converted into velocity pressure and then calculated with the track area to Q, that is the flow. And the power curve, it is here in BHP, that is the green curve. So the power curve is the measured power either directly from the panel board, or it may, the amps may be amps, power factor and all this may be individually recorded and then calculated. The input power may be calculated. From the parameters of both this curve, you can arrive at the efficiency curve using the efficiency formula. So this is going to be a test block condition of your fan. But when you put it onto the system, that is wherever you have installed it, it may not be exactly operating at that point what is mentioned there on top with the two dotted line from the x-axis and y-axis on the performance curve of the fan. It may not operate there. It may be shifted either to the right side or left side or to the bottom, depending on the system. So how the system is designed. And the red color curve, what you see is a system resistance curve, which I'll explain you in the following slides. So the system resistance curve is completely independent of the fan performance curve. This is a very important point which most of the people may not be aware of. They may think that the fan operating conditions at the site where the fan is used will only fall on the performance curve, that is the test block performance curve. No. The system resistance curve is just completely an independent curve. The two curves intersect at one point where fan performance meet the requirement of the system. That is the dark curve which I showed, dark point which I showed you. System resistance curve is described by the equation P is proportional to Q square. P is proportional to Q square. In case you want to enhance the performance or you want to decrease the performance of the fan, then you have to only go by this formula. This is the system resistance curve and the fan curve. So you have an operating point. So when you throttle this fan or reduce the RPM, that is by using a VFT, so your point will only fall as you reduce the speed or throttle the inlet vane control. Your point will fall on the blue curve only and not on the red curve. And as I told you in the previous slide, this point, operating point, will not be exactly as it is mentioned in the performance curve, because it will vary depending on the pressure in the system. For example, let us consider an ID fan where the pressure is 300 water column designed for and 10 meter cube per second. So this point, operating point, is falling on 10 meter cube per second and 300 water column. But when you go to the side, you have different resistance on the inlet of the ID fan. For example, you may be maintaining -5 to -10 water column in the boiler furnace, and then you may come out and there might be a economizer where it is a resistance. You will need some pressure drop across this economizer, and after that you have the air preheater where again that is a resistance. You may need certain amount like 40 or 60 water column for that, and then it goes to a ESP. Again, that is a resistance, and all the interconnecting ducts have resistance. So you have designed this fan for 300 water column, say if suppose, but the total resistance now measured there is only 250 water column. So your pressure has dropped. Then what happens in that case? Your flow increases. When the pressure drops, your flow increases because that operating point may shift to the right hand side on the red color curve, that is the fan curve. So in order to control that flow, what happens? You may have to use a damper, either in the inlet, which is not advisable, or sorry, in the inlet which is advisable, or in the outlet which is not advisable, or a variable frequency drive, or a variable VSD, variable speed drive, in order to get the 10 meter cube per second, because anything excess of that will create a cooling into the furnace. Okay, and it may be absorbing more power also. So we need to operate it at the optimum point, so at 10 meter cube per second. So this is how the point gets shifted. So you have to be very careful when sizing a fan on the fan manufacturer side as well as on the boiler designer side. When they arrive at the parameters, when they calculate the resistance across the system, they should not be considering a very high factor of safety. Like if they want to have, they arrive at calculate around 60 pressure drop across the ducting, they can consider it something around 5% as a factor of safety, not in the range of 30-40%, which is going to affect the system drastically, because once they add for the ducting and then for the ESP to the air preheater to the economizer, and all these add-on percentages added on will be very high, and that is going to become like when you require 250 instead of that you'll be designing a fan something at 300 or 350 So higher factor of safety, arriving at higher factor of safety, it's going to decrease the efficiency of the fan. Similarly, when a fan designer is going to design a fan, they should also not consider any factor of safety on the performance, but they can consider factor of safety on the mechanical strength of the fan. That's not going to happen anything with the power. But when you increase enormously the power or factor of safety on the fan, then you drop in the efficiency. So always there is on the minus side for the volume, and for the power and volume, power and pressure 5%. So you can always be safe in designing the fan with the right parameter asked by the customer. Fan loss. See, the fan loss or the capacity is directly proportional to N and D cube. N is the RPM, so it is directly proportional to the change in the RPM, and it is directly proportional to the cube root of the diameter differences. So pressure is directly proportional to N squared and D squared. Power, capital N power, is proportional to N cube and D to the power 5. So when we size a fan by diameter, we use this formula on the standard diameters of the standard designs, and to arrive at the RPMs, we use this formula. So these formulas can also be used by energy auditors when they find that a fan is delivering more volume of air, maybe it's a bigger oversized or it's a small size, then they can use these formulas in altering the RPMs without considering the D. So they can use this formula in altering the RPMs to arrive at a better performance and efficiency. In case they want to change the diameter by a margin and try to reduce the power because it is giving higher capacity or higher pressure, then they may use this formula on the D side. Q is proportional to Q, P is proportional to D square, and N power is proportional to D to the power 5. So with this, you can arrive at the diameters and the RPMs. So now we go into the energy conservation point. So before going into the point, can I ask you if you have any doubts on these selection procedures of fans? Because I would like to say something on that. Okay, let me first complete that. The poor initial system design or the fan design contributes more on the loss of efficiency. Likewise, a tailor-made fan, what we call it. So you design particularly for the parameter like volume and pressure, and you maintain an efficiency something where more than 80%. But whereas when you have standardized size fans, like you have a size 710 and 800, and your fan will not be accommodated in 800 because the efficiency will be, the fan is bigger and efficiency is low, and you cannot accommodate it at 710 where your efficiency is again low because it is smaller in size. So what happens? You are in between. But some companies, they don't supply you anything in between. They'll say either take this or take that. So there you are bound to compromise on the efficiency, thereby on the paying your energy bill on the power consumption. So it is always recommended you buy a fan only with the peak efficiency. So on the selection of the fan, you have to see to that you are also getting a fan, because when you have two standard sizes, you may not fall at the 4 RPMs, that is like 8 pole RPM, 6 pole RPM, or 4 pole RPM or 2 pole RPM, which can be directly coupled. Because when you couple, your energy loss for the coupling is very less. When you go for a belt drive, you will lose more power, more energy. So these points have to be considered. So the sizing of the fan is very important, and sizing of the system. When you come to the sizing of the system, you can take a cement plant where you need some velocity to carry the dust particles. But most of the plants, if you see in the olden cement plants, the velocities are very high. So every particle, they have certain carrying velocity required. For example, wood dust can be carried with a velocity of 14 meter per second. And when you go for cement dust or some raw mill dust, you need around 18 meter to 20 meter per second velocity. But when the total duct system is itself designed for 20 meter per, 25 meters per second or 24 meter per second, one thing you are sure that your cost is coming down because your duct size will come down. But when you go for bigger duct, the optimal velocity where your dust can be carried, then your pressure drops are going to be minimized. When you go for higher velocities, you have two problems. One is your energy, that is your pressure drop across the system is going to become high. So you need more static pressure. So you will be requiring bigger motor or more energy will be consumed. And the second point is there will be erosion in your ducting because of high velocity. And when there is erosion in the ducting, you may have to frequently change the ducting. And because of these erosions, the flow path is not smooth. So that may also increase the friction more. And once the erosion has started and the surface has become rough, automatically depositions also take place. So it's going to be a big problem. When the deposition again increases in the duct, again the duct passage area is coming down. So when this comes down, again your pressure drop increases. So designing a system, total system, that is a duct, maybe the ducting or any pollution control equipment across the system or any preheaters or whatever it is. First thing we have to see to that the optimum velocity what is required is maintained. It is not on the higher side. It should not be on the lower side, then it may not carry the particulate. So this is one point which we have to be very clear on to. And the going by the drives now, we are using frequency drives, and then for the pulley side we are going on the flat belt drives. So it is so alarming that we have been talking of the flat belt drives, but mostly today not even 15 to 20% of the fans are having these flat belt drives. Still wedge belt drives are only into usage because of the high cost of the flat belt drives. But whereas the savings are there. So we have to consider into these small things in the design stage. But what to do in the operational stage, I will come to you on the later slides. So the major energy consumers are cement, paper industries, metallurgy, fertilizer, thermopower plant, and sugar plant. The metallurgy industry includes whether it is a copper smelter, aluminum smelter, steel complex, anything that is metal. So the energy consumption of fan amounts to 10 to 25% in all industry. The possible energy saving could be up to 25%. We have achieved up to 35% in the tobacco industry, in the tobacco threshing industries. The tobacco threshing plant, what you see from Ongole to Guntur, Adroit Fantech have extensively done energy studies on fan performance studies and conserved power up to 35%. So there was not a big deal. It was only the fan sizing was very big. We had to reduce them, and we also reduced the duct velocities. So only by this two, changing the fans to high efficiency fan and designing the fan to the right requirement of the by capacity and the static pressure, bringing down the velocity also, we were able to achieve a power saving of up to 35% in the tobacco industry. So these are the industries where major power fans are there, power consuming fans are there. So what are the parameters that have to be considered? Volumetric flow rate, pressure head, temperature and density. See, if it's a normal hot air, then the temperature alone will do. But if it is going to have in the case of fertilizer industry or in the case of some chemical handling industry, then we need the composition of the flow medium to calculate the density, because the density plays a vital role in designing the fan size. based on the pressure. The medium to be handled. This is mainly for the case of whether we need to go for special coating on the blade for erosion, or special coating like FRP, FRV, or go for special material as SS304 or 316 in case of acidic air. So only to ascertain on that part of it, we ask for the medium to be handled. Then the space limitations. So the space limitation also, when you go for slower speed, because the slower the fan speed, the erosion is erosion is lesser. So in that case, when we consider if there is no space, then we may have to discuss with the client and find some other place which may not be recommended by the client. So we ask in advance what is the space limitations there. Of course, the cost part of it. So the cost part of it plays a major role for the client, because they are very particular on to the cost part only. So that is the reason today we are not seeing the VFDs in major industries. Still they are running with a single speed motor. We are unable to see flat belt drives and all those things. Reasons for higher power consumption in fan. As I told you, improper sizing and selection of the fans. So the selection of the fans can be basically on the type of industry and application. So the application is calls for, you can go for a higher speed fan, then you can go for a higher speed fan. And if you are going for slower speed fan, you can go. So all this, the selection is basically, as I told you again, the optimum efficiency is very important. That is static efficiency. You have to calculate whether the fan will deliver the parameter for the efficiency. So all this is very important. And also the outlet velocity of the fan. Nowadays, like for an air conditioning, they specify it has to be less than 8 or less than 10 meter per second. So the selection type of blades to be decided. So the improper sizing and selection of fan is very important aspect. Fan operating with dampers for various process load condition. So if you have 2-3 MCR points, like mean continuous rating, maybe you have 2-3 operating points for your process. Maybe one is design, then one operating point, or then you say another offset operating point, like 2-3. Then it is very difficult to arrive at the at that each and every operating point with dampers. Drive arrangement like belt with the higher slipper. Yeah, that means the belt is not properly aligned, the tension is not proper, then you will have all this problem. Leaks in the duct and system. Very important aspect which is being mostly ignored. Suppose you have a fan of 10 meter cube per second and the pressure measured, not designed. The pressure measured is around 200 mm water column. Then what happens? Suppose there is a leak and the leak is around 10%. That is 1 meter per second. So 1 meter per second into the same pressure 200 mm divided by 102 divided by the calculated present efficiency and the turning point will give you some power, and that power is a loss again for you. So you need to plug all these leaks effectively in order to arrive at a better efficiency. Inlet and outlet obstructions. I have a slide which I will show you at the end of the session, almost close to the end, wherein you can see the inlet and outlet obstructions also plays a vital role on the efficiency and for higher power consumption. Higher motor rating than required. So people may tend to say, I already have a motor of 100 kilowatt, whereas his requirement is only 75 kilowatt motor. So when you go for a 100 kilowatt motor and your input power is only like something around 60 kilowatt, so your motor is operating at 60% load. So the efficiency normally tends to drop. So motor at its full speed or full rating only, particularly at its full rating only gives it higher efficiency. When the rating is below, then the efficiency drops. So you can refer this into the motor data sheet where it will be very clearly mentioned that at 25% load, 50% load, 75% load and at 100% load. So the efficiencies are only peak at 100% load and it will be reducing at 75, 50 and at 25 meters. So with this, can we break for a tea and then join back? Oh, yeah, it will be around 10 minutes time we can give and we can resume back. So till then, you all may relax. Okay. Huh?
மேல வந்தேன், சரி அப்படியே மேல வரலாமான்னு பார்த்தேன். சரிங்க பிரதர், நான் டிபார்ட்மெண்ட் வந்துட்டேன்.
அப்படியே பேசுறேன். So hope all are you back. So let's continue with our sessions. So the next part of it would be how to audit fan. So first and basic prime thing would be to collect the fan nameplate data, fan curves available, fan gear drawing available with us with the customer, and the motor nameplate data. If motor data sheets available, that also. And the system layout. We need to get the system layout, or we need to just make a hand sketch of the system layout, and in order to ascertain the measuring points and all those things. Measure motor input power directly from the control panel. Measure fan and motor speed, which is one of the prime factor, because any easy modifications to arrive a parameter, only the motor speed is we can handle very easily. We can handle it. Measure static pressure at various points of the system. So this is very important, because this helps us to ascertain where the pressure drop is in excess than the normal. Like, as I told you, let me go to the same example, the boiler ID fan, minus 5 to 10 mm, minus 5 to minus 10 mm water column in the furnace, and then there is a ducting, then you have an economizer. So the economizer will be having a pressure drop of something around the 60 mm water column. So anything you measure before the economizer is the furnace pressure drop. Anything you measure after the economizer will be the pressure drop of the economizer as well as the furnace. You minus the reading after the economizer with the reading of the furnace, you will get the pressure drop across the economizer. Similarly, you measure the pressure drop after the air preheater, so you can ascertain what is the pressure drop across the air preheater. And then the ESP, after the ESP, that is before the fan, and then after the fan. Normally after the fan, sometimes you may have a minimum pressure drop of 10 or sometime 20 mm, or sometime you may have those reading in minus. In that case, you should ignore that reading, because that is the reading, not minus pressure drop draft, not generated by the fan. It is been generated by the stack. So you should take only the other readings. In the suction side, yes, of course, it is going to be in the minus only. So when you have all these readings, for example, if the air preheater supplier has mentioned a pressure drop across as 60 millimeters of water column, and whereas now it is, and when installed newly also, if they would have checked and it was consuming something around 50 or 55 mm water column, but now in this case it has gone to 75 mm water column, then there is something clogged there. either in the system or at the inlet of the system, that is particularly in the air preheater. Or sometimes even in the duct bends, you may find the bends are very acute and the pressure drop across the bends may be very high. So as initially told that it is possible to reduce the energy by modification the process lines, you can achieve some amount of energy savings. So when you measure the static pressure across all these points, you will have an idea which part of the line or system is consuming more energy. That is energy here in the sense static pressure. Okay. So it is very important to measure the static pressure at various points of the system. Estimate the capacity. So the capacity, you are going to measure the dynamic pressure or the velocity pressure at the inlet of the fan. We normally recommend not to measure it at the delivery of the fan, because always the delivery of the fan has higher velocity than the inlet of the fan. And in the inlet, you may have a duct piece where you have a longer length, so where the flow is little uniform. You can't say it will be laminar flow, but it will be uniform. Whereas in the delivery, towards the outer circumference of the casing, your velocity will be high, and toward the inner side of the circumference, the velocity will be lower. So you may not be able to get a proper reading out of it. So that is why we always recommend to take the velocity pressure or the dynamic pressure at the inlet of the fan. Once you ascertain the capacity, I mean, by from velocity, the velocity, and then you know the operating temperature, you know the track diameter. So you can calculate the velocity from velocity pressure, you can convert it to velocity, V squared rho by 2G, using that formula. So you get the velocity. Once you get the velocity into area, you will get the capacity. So the area into velocity will give you the meter cube per second. That is the capacity of the fan. What is the delivery? So with that and the pressure measured at the inlet of the fan and outlet of the fan. Fan outlet static pressure minus the inlet static pressure will give you the pressure developed across the fan, flange to flange. So into that, divided by 102, divided by the input power measured at the panel board, will give you the efficiency of the fan. And check the fan operating point with the curve. So suppose you have a curve, that you can see a curve there, that is in dark bold black, and there is a system resistance curve, and in dotted lines. So you have three parameters I have just marked: A, B and C. So the point where the performance curve and the system resistance curve meet is the operating condition as per test block. But if your fan is operating at A, then it denotes that your system resistance is low, so higher volume. So your fan is little over designed, or you would have designed for that. It would have been designed for the thing, but your system is not designed for that. Your system is having a lower resistance. But when your operating point is at B, that means your system resistance is higher than designed. In that case, the flow comes down. But if your operating point is at C, then your fan is over designed. Okay. So this is what I have mentioned in the next slide also. Fan operating zone at A indicates leak or lower system resistance. Zone B indicates higher pressure drop due to plugged or undersized system. Fan operating zone C indicates fan is oversized. So this will give you, once you get the curve from the client, and you measure the parameters and you mark on the test plot condition curve the point what you have measured, then you will understand what is this condition of the fan. Either it is A, B or C. Mostly it is A or C. So the 5-point formula for energy conservation is match demand and capacity. So what you require, you have to match the capacity with that. Avoid unnecessary demand. That is what I told you earlier, that you should not have higher factor of safety which will affect the performance by way of efficiency and higher power consumption. Select correct drive system. Your drive system should not be inefficient like old model of V-belt pulleys. Wedge belts are far better, and we always recommend flat belt for better efficiency. If not, if you can select a fan at 1440 or at the synchronized speed of 2 pole, 4 pole and 6 pole and 8 pole, then it would be a direct coupled. In a smaller size fans, it can be directly mounted on motor shaft where your losses on the drive arrangement is minimized or even reduced if you go for a direct mounted on motor shaft. Use energy efficient fans. We also recommend, as I have also told you, that whenever we procure a fan, we have to see to that the efficiency, static efficiency of the fan is at the highest. Not something what the supplier give you at 65% and 68%. If that can be improved, it is always better to buy a fan, because that whatever energy you save, it is going to save you in terms of money. We also recommend to have energy efficient motors. As today you are having IE2, IE3 and even IE4. So the efficiencies of the motor is also increasing. So when that increases, automatically you again save on power. So match demand and capacity. Selection of correct size fan in terms of H, that is static pressure, capacity and efficiency. We have come across many people even today, after so much of education on the energy conservation, power bill and all those things, but still people come and ask us, fans, sir, give me a 5 HP fan, give me a 10 HP fan, give me a 20 HP fan. And they don't understand that you can give fans in 5 HP or 10, for example 10 HP. You can give a high pressure fan and a low volume fan. You can also give a medium volume and a medium pressure. You can always give a high volume and a low pressure fan. So QH and efficiency are very important. Kilowatt and HP are not important, as it is a function of QH and efficiency. How to match the flow and head? That is flow control option, outlet damper control, inlet vane control, variable speed drive. It's very important to understand these three control systems and how they contribute in energy saving or they don't contribute. This is inlet vane control. Just to make you understand, it is called as variable inlet vane or inlet vane control, or it provides a pre-rotation or spin to the incoming flow in the direction of impeller rotation. This is very important. Very essentially, it is to be located only at the inlet of the fan, that too very immediately at the fan inlet flange, not somewhere else in the inlet line. And this inlet vane at every position, for example, it is 100% open, it is a free flow, it has got a curve, and at 75% or 50%, 60% or 40%, 25%, it generates a family of curve. I mean family of curve in the sense volume versus pressure, volume versus power. So it generates a family versus family curve, which we will see in the following slides. Now, fan performance with outlet damper. So you can see there is a parameter where the that is called as a fan parameter curve in dark line, and the dotted line denotes the system resistance curve. So your operating point is coming down. So once you use an outlet damper, this outlet damper is nothing but a resistance. It throttles your volume and then what happens? The power is not reduced. The power is not reduced. The actual operating parameter is PF, that is not where the dotted line is intersecting. The next to that on the left hand side, that is the actual operating point. But it is operating at PS now, that is at the system resistance curve below. That you can see a vertical dotted line denoting the loss in the pressure. So the power is same. So you will be losing much on the power. That is, you can say, in other words, you are killing the energy with the outlet damper. So we normally don't recommend outlet damper in the fan for flow control. It is only used to isolate the fan in case of any service has to be taken. Fan performance with IVC, inlet vane control, or variable inlet vane, both is the same. So as I said you, here it denotes a family of curve. You can see the first curve at 90% opening, and that is 90-degree opening, that is 100%, then at 70-degree opening, at 50-degree opening, at 30-degree opening. Similarly, it will follow with a power curve, a different power curve for every degree of opening. So here, when your operating point is at PF and you are operating at PS, automatically at 70-degree opening, you are able to throttle. So at 70-degree opening, if you see, there is a decrease in the power. So by using an inlet vane control, you are saving some amount of power. So this is one method and the cheapest method of controlling the flow in a fan, whereby you save some amount of energy. Fan performance with the VFD, the variable frequency dial, where you can vary the speed. Now you have two curves here, so that means it is full speed and the curve at the bottom is partial speed. So when you want to operate at a parameter at a partial speed, you achieve it. And that parameter, you see both the curves are parallelly coming down, one parallelly down. And the power curve is also, you can see there is a very big change in the power. So you will have a good power saving, a best power saving with the help of the VFD. And the efficiencies will not be altered much except for 1 or 2 units. This is to explain you about the outlet damper and the inlet vane control, or the VIV, how the power is saved. For example, 400 meter cube per second, 300 mm water column, and the fan efficiency is 81%. Then your power absorbed is 1452 kilowatt. In condition 1, you use the outlet damper to control the flow, to bring it down to 350 meter cube per second at 250 mm water column. So what happens, as I told you, you kill the energy, but your power is not coming down, your efficiency dropped, your volume dropped, your pressure also dropped. So you required only 350 and 250 mm water column and you got it. But what happened? The energy is killed. It consumes the same power, 1452 kilowatt, that is 1452 kilowatt. But in the condition of a variable inlet vane control, you can see you are achieving the same parameter, 350 meter cube per second and 250 mm water column at an efficiency of 66%, because that has a different power curve. It generates different family of curves for different opening conditions or opening degree or opening percentage. So whereby your power absorbed is only 1300 kilowatt. So energy saving is 152 kilowatt using a variable inlet vane control. Therefore 10.5% is the power saving directly just by understanding what damper to use for flow control. Use of VFD is most effective. As speed is reduced, flow and head are also reduced. Therefore, reduced power consumption. Fan efficiency relatively constant. There is no alteration in the fan efficiency. Reducing the speed by 50% typically results in a reduction of efficiency by 1 or 2 percentage points. This is because once the speed is reduced, your motor efficiency also marginally drops. And in the parameters, in the fan, as per the fan curves also, 1 or 2 percentage points you reduce. This denotes the kilowatt versus the speed versus kilowatt. As the speed increases, your kilowatt raises. As I told in the fan loss earlier, that when the speed changes, the kilowatt raises to the power 3. VFD, how efficient it is. So we have calculated, which will very easily explain you what happens once you use a VFD. See, the operating condition, you have 2 operating conditions, design and MCR. The capacity at design is 40 meter cube per second and 35 meter cube per second at MCR. The static pressure in mm water column is 300 mm at design, and the operating mean or continuous rating is 250 mm water column. Operating hours is going to be 500 hours in the design condition and 6,700 hours in the MCR condition. Now, please note on the fan speed. In design condition it is 760 and we are reducing that to 660 in order to achieve the parameter of 35 meter cube per second and 250 mm water column in place of the design parameter 40 and 300. So the power absorbed at design is 145 kilowatt and at MCR condition is 105 kilowatt. So calculating the on hourly basis, considering 4 rupees per unit, the cost, energy cost is 2.9 lakhs for design condition at condition for 500 hours, and for MCR condition for 6,700 hours it is 28.14 lakhs. So the total power in terms of rupee consumed was 31.04 lakhs using a VST. Without a VST, if you were to use an outlet damper, then you have to multiply that 145 into 500 plus 6,700 hours into 4 rupees a unit will give you 41 lakhs 41.76 lakhs. So the saving is 10.72 lakhs. So this is how the VFD is efficient. So remedies to overcome power loss. Ensure the inlet and outlet obstructions are minimal. I will explain you with a slide which is following. Use inlet vane control. So remedies to overcome power loss. Ensure the inlet and outlet obstructions are minimal. I will explain you with a slide which is following. Use inlet vane control to throttle or VFD for various process loads. So when we talk about various process loads, and if you are using a VFD or a inlet vane control, You can automate the inlet vane control and the VSD. I mean, you can connect this together. So based on your process load, they can be programmed to vary the speed or vary the damper conditions. So they can be automized. So wherein you don't need anybody to control it, automatically it can be looped with the panel board with the VFD or the actuator to operate the damper. So that as you need to select a point. Suppose it is a ID fan, then your operating point will be the negative draft in the furnace, like 5 to 10 mm minus on the minus side. So to maintain that, when you maintain that, automatically your variable frequency drive will change the speed of the fan, or the damper controlled fan will have its damper automatically throttled. So if you use this interlink, this arrangement, have this interlink in the system arrangement, then you will save more power. Change the fan with the high efficiency fan. Yes, still there are a lot of fans with low efficiency, lower blade configuration, or some sort of what to say, mismatch in size. Something is there. Those fans should be replaced with high efficiency fans so that you can save enormous amount of rupees. Use of high energy efficient motors. Yes, now you have, normally we are using now IE2. Now there is IE3, IE4. There is a very good changes in the improvement in the efficiencies, and these are going to give you power saving. Minimize duct and system pressure. So as your duct length is minimized, not the size, the diameter of the duct, the length of the duct is minimized, then your system pressure is also going to be minimized. Thereby you can operate at a lower kilowatt. Use of low slip belt. Ensure fan intakes are smooth and rounded. Clean screens, filters and blades regularly. This is one aspect which is not done. So the blades of the fan needs to be regularly cleaned. The filters particularly and screens particularly have to be filters, because once they are clogged with the dust, they need more pressure in order for the air to pass through, and that is going to increase the energy. Lubricates bearing regularly. Now you can see this slide. The inlets, if the inlet is in a direct in a 90-degree, you know what is the condition. The flow, there will be some pressure drop which will be more than the round bend, and when you have a long radius bend, it is going to be more better. And from diameter you reduce it near the fan, then there is going to be more losses into it. This is the fan inlets I am talking about. This is on the axial flow fan side. If you have a direct flange end, then you have this space, that red mark, where you will find there is a recirculation over there. Whereas if you have a coned mouth, then the flow is good into it. And having a bend like what you have at the left hand side corner in a centrifugal fan, then that is also going to have some problem. It may consume more power. The flow passage may not be smooth. But whereas when you have a conical inlet, the flow passage will be smooth. So this slide shows you how your outlet should be. See, in a centrifugal fan, the top portion, if you see the left hand side slide, the top portion of the casing outlet will have more velocity than the bottom of the outlet. In that case, when you make your flow, what is in the second slide, in between, middle one, when you make it that way, there will be lot of losses, energy losses. But if you make it the other way, what you have in the third one, it will work. So either the first and the third slide is best. But what is in the second, you cannot install a fan in that position where your losses will be very high. There are other factors where when the fan is assembled or sometime you remove them for maintenance and put it back, or when we audit the fan, even these things have to be checked if we can, if it is possible. Because higher cone gap, this clearance in the cone, higher cone gap, inlet cone and the impeller mouth, the higher the gap, the recirculation is higher. So then your efficiency will drop. The minimum the gap, your efficiency is better. So you have to maintain a uniform cone gap, all 360-degree, all around the circumference of the inlet, as well as the clearance should be as minimum as possible. In the case of the axial flow fan, this is the radial clearance, running clearance, that also has to be minimized, because if that is not minimized, then you will have the same recirculation problem over here. So we got to understand one thing, that the capital investment on these fans are going to be only 5%, whereas the operating cost over the years is going to be 95%. And we should not interchange fan. Each fan is designed, it is actually tailor-made for every application and every parameter. So like for 300 meter cube per second and 500 mm water column, there is a fan. But you have a requirement of something around 250 meter cube per second and 400 mm water column, you cannot take that fan and put it over here. So it will operate at a part load, and then it will consume more current, be consuming the current of the higher capacity and pressure, and you will be losing your power as well as your routing. Hope you all had a wonderful guided tour, and if there is any queries, you can please you can have a internal discussions among us. Any doubts, you can start asking me. And before that, I thank you giving being so patient in attending to this session, and also I thank on behalf of IES that for all of your participations, and hope this program is giving you a wonderful idea on various aspects of energy conservation in various equipments. And you can always feel free to write to IES and or to the concerned session whoever has taken the sessions. So we all will be very happy to interact with you even in the future, either through the WhatsApp or through the email. And it was really very happy to be with you all. And thank you so much. And if there is any queries, you can right away now ask. So I'm at your service.
Participants, if you have any questions, you can raise now.
Unmute பண்ணுங்க. Hello. Okay. Anybody can hear us?
Sir, excuse me, sir.
Yes, sir.
Sir, can we have discussion on the blowers here, sir? Like on the blowers?
Yeah, you can ask me your question, sir.
Yes, sir. Sir, like in textile mills, by spinning mills, certain they use some pneumophile casing blowers in.
Okay.
The blower design, the casing design is different, but we had an audit in that particular textile. We found a lot of recirculation zone and the drop in the flow rates also. They could not maintain a sufficient pressure at the individual spinning mills in.
Okay.
So whether you have any experience or any insights on this pneumophile casing blowers, have we got any input, sir?
No, I don't deal with the textile, but see, for a centrifugal fan or a blower, they need to have a volute casing. If the volute casing is the one which generates the pressure, okay, because in an axial flow fan, the blades the aerodynamic shape generates the pressure or the energy. But whereas in the centrifugal fan, the velocity over the outer side of the volute casing only generates the pressure. But when you don't have a casing design properly made, you may not be able to achieve, or you may have to oversize the fan impeller.
Okay, sir. Okay, thank you, sir. Okay.
Any other questions? So participants can be close with this. My WhatsApp number and email ID is available here. All of you are free to contact me anytime on the WhatsApp or the email. If you have any queries or any application oriented studies required at your place, or if you need any advice on procurement, I will be happy to assist you. Okay, thank you very much for all your time, and we all meet again sometime. Thank you so much.
Thank you.
Okay, thank you.
Thank you very much. I have posted the feedback attendance form in the WhatsApp group as well as to your registered email. So please submit that. We will meet you tomorrow. Right. So tomorrow is the final day. So and also we will update about the test in the WhatsApp group as soon as possible. Thank you.
Thank you, sir.
Thank you very much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.